Okay, on to part C of our momentum in two dimensions videos, and onto the holy grail of conservation laws, the conservation of momentum. So I say that because momentum is always conserved. Energy is sort of conserved in an elastic collision, but in elastic collisions we can lose energy in lots of other forms. Mass is normally conserved, say in a chemical reaction, but we know, or we may know, that in some of the nuclear type reactions we can get this conversion between energy and mass. So it's really our mass energy conversion law, more strictly speaking. But momentum can be regarded as a conservation law. And it really lets us understand and predict and explain lots and lots of interactions, whether they are collisions, whether they are explosions, or variations on explosions such as spacecraft and rocket propulsion and that sort of thing. Let's get into it. So we're going to start out by deriving an expression for the conservation of momentum for two interacting particles. This can be applied to 3 or 4 or any number of particles, but we're just going to look at a simple case where we have two particles interacting, like we started off with looking at the two cars on the track, the red and the blue little car in the first video. And our starting point is going to be Newton's third law, which says for every action force, there's an equal and opposite reaction force. So for every time one of the cars applied a force on the other car applied an equal and opposite force back on that car. So from the third law, I think we'll just say from the third law, I think we know they're Newton's laws by this point. We know that for every force, there's an equal and opposite reaction force. Now we know from what we've just looked at that force can be considered as the change in momentum of object 1 over the time for that change, and this can be considered as the same for object 2. Obviously we can cancel out the times there, so we get left with the change in momentum of object 1. So if we're thinking about those cars, the change in momentum of the blue car in a collision will be equal and opposite to the change in momentum of the red car. Another way we can write that is change in momentum. I'm going to bring this over to this side, so we're going to add, to get rid of the minus P2 there, we've got to, so delta P2, negative delta P2, we've got to add delta P2 to this side. So basically what this expression is saying is the total change in momentum of object 1 plus the total change in momentum of object 2 must be equal to 0. So that is that the total change in momentum must be equal to 0. So if we say what I've just said there in blue in words, we'd say the total change in momentum in any collision or explosion is equal to 0, i.e. momentum is conserved. It cannot be created or destroyed. So if we want to sort of look at that scenario, and this is how we'll often, when we do a problem, we will look at the total initial momentum on one side, and then we will look at, we'll know that that must be equal to the total final momentum. And I'll go through some problems so you sort of get to understand what we mean by that. Just quickly, the total initial momentum must be equal to the total final momentum. Let's get on and do some problems. Okay, let's look at a collision. So what we need to be able to do is compare the magnitudes and directions of the total momentum vectors before and after a two-puck airtable collision recorded using a multiple image photograph in order to show momentum is conserved. And we only need to consider only examples in which the mass of one puck is an integral multiple of the mass of the other puck. Ignore the scale of the photograph, the flash rate, and the actual masses of the puck. So what that's just a way of saying is that it'll always be a simple situation where, say, in this case, puck A is twice the mass of puck B, 2m, or 3 times the mass, or 4 times the mass. You wouldn't get like 1.5 times the mass, or 1.8 times the mass, or a number like that. It would always be a whole number. So this diagram represents a multiple image photograph taken from above, like an air hockey table. So where you've got one puck on an air hockey table interacting with another puck, in this case puck B is stationary initially, and we're looking at that interaction in the same way we talked about multiple image photographs when we did projectile motion. You have a strobe light flashing at a regular time interval, so the time between each of these images is always constant. So if the distance moved is constant, that shows that the velocity is constant. Remember, with projectile motion we saw the distance increasing and increasing for a free falling object, indicating the object was accelerating. Well, here the distance is constant, so the velocity is constant, at least in the before situation and the 2 after situations for each puck. So, first thing that we need to do is represent, so firstly, just in terms of this question, the motion of the 2 pucks on an airtable is shown in the multiple image diagram below. The mass of puck A is 2m, the mass of puck B is m, so it's half puck A. Puck A is initially moving in the direction shown before it collides with puck B at this point, which is initially stationary. After the collision, the pucks move in the direction shown. The time between each image is constant. So let's consider, and we'll use green again, our initial. What is the initial momentum of puck A? Well, obviously it's going in this direction. Now, because it has a mass of 2m, we're going to draw that initial velocity vector for puck A across 2 intervals of the ball. Because if you like, momentum equals m, the mass of A, times v, and the mass of A is equal to 2mv. So the way of showing that double is drawing that across 2 images of the ball, because it's got double the mass. If we look at the after, we'll look at B first. Because it's only got a mass of 1m, so this is the final momentum of puck B, that only goes to represent one velocity unit, if you like, one section of time. And if we look here for puck A after, once again it's got twice the mass, so we draw that over 2. So this is mass, the final momentum of puck A. So the initial momentum of puck B was 0, so we can't really draw that vector for that. That was basically the would be 0, so it doesn't really come in. So if you like, on this side we've got our initial momentum. Over on this side we have the final scenario. Now, what conservation of momentum? Firstly, we've done part A. On the diagram above, draw and label momentum vectors for each of the 2 pucks after the collision. So puck A final, puck B final after. We've done that. The next part says, with the aid of a vector diagram, determine whether or not momentum is conserved in the collision of puck A and puck B. Justify your answer. So to work out, well, the total initial momentum is just equal to the momentum of puck A. So the initial momentum of puck A. So that if you like, is equal to the total, so T for total, initial momentum. The total final momentum is equal to the momentum of puck A plus the momentum of puck B, which if we look here at this diagram, we draw a line parallel, same length as puck B, we get that. So the final total momentum is given by adding those two vectors together. So that is PFA plus PFB. Now I haven't put little vector arrows above each of these. I did get a question in class about this. If you're drawing vectors, you clearly understand they're a vector, so it's probably not critical. Makes my diagram look a bit neater as well. So if we look now, that's equal to our final total momentum. So if we look now, our total initial momentum is equal to this purple vector for our total final momentum. But we need to really be a little bit more specific than that. They are both the same length. They are both going in the same direction. Therefore, we have shown that the total initial momentum is equal to the total final momentum. That's the important part in terms of justifying our answer. So, just for completeness, I could either do this with formulas or words. I'll do it with words. The total initial momentum vector, which was that is a lowercase t, E is equal to the, actually that's not words, that's symbols, is equal in length and in same direction as total final momentum vector, which was PTF, showing momentum conserved. Okay, so I forget if I said at the start, this was actually a question from last year's exam. So the collision question won't always be to show that momentum is conserved. However, hopefully by understanding that process, you could tackle various variations of that question. Thanks.